In this section, we're going to be discussing the difference between mass and weight. Now, in just general everyday terms, when we talk about our weight, we're really talking about how much of us there is. And if we think about, oh, we need to go on a diet, it's because we think there's just simply too much of us. And we would think there was too much of us whether we were on Earth or whether we were on the moon, and it wouldn't make any difference. So we want to get away from your preconceived notion of what weight is when you're talking about physics, because there is a very big difference between mass and weight. So if you look up here, I have some differences listed between mass and weight. First of all, mass is simply just how much matter there is in an object, how many atoms, how many molecules, how many particles are making up that particular object. Weight, however, is how hard gravity is pulling on an object. So it is a force. Again, because a force is a push or a pull, we're talking about how hard gravity is pulling on that object. So while you have a certain amount of mass, your weight will vary depending on where you are. If you're on the moon, you have much less weight than you do if you're on the Earth, although the mass of you, how much matter there is located in your body, that part does not change. So because weight is a force, we had talked previously how a force has a direction, so therefore weight is going to be a vector quantity, while mass is simply a magnitude only, and it's going to be a scalar quantity. The example I gave you about whether you're on the moon or whether you're on the Earth and how that's going to change your weight, obviously then weight will depend on location, whereas mass does not depend on location. The amount of mass that is within you is going to be the same no matter where you are. The units that we use for mass and weight, again, we talked about this real briefly earlier. So units of mass are going to be in kilograms, could also be in grams or milligrams. If you're in the English system, it's going to be in slugs. And we're not talking about the little slimy creatures, it's a different kind of slug. And then the weight, if you're in kilograms, and then you're going to use an acceleration in meters per second squared, as we talked about before, in order to give you newtons. If you're in the English system and you're using slugs as your unit of mass, in the English system we normally use 32 feet per second squared as the acceleration due to gravity. And so if I use that acceleration, then that's going to give me pounds in my weight. So in order to calculate force, we already know that force is equal to mass times acceleration. Well, I'm just basically changing the letters around a little bit. The specific force that I'm talking about is going to be weight, so I change it to a W. And this particular force has to do with how hard gravity is pulling on an object. And so in place of A, I use a G to indicate that I'm using the acceleration due to gravity for this specific object. So 4 key differences then between mass and weight. I'm currently standing out of the way, so if you need to pause the video in order to jot any of those things down, this would be a good point to do that. I'm now going to work both examples 5.2 and 5.3 in case you need a little extra explanation of those. So we'll make some space up here for that. So example 5.2 says a man steps on a scale and determines that he weighs 151 pounds, which is equivalent to 672 newtons. Determine the man's mass in both kilograms and slugs. So again, a pretty straightforward application of our equation that weight equals mass times gravity. And so if he weighs 151 pounds, and I'm trying to find out what his mass is, since this is the English unit, I need to use the fact that gravity is 32 feet per second squared. And so then my mass, when I take 151 and I divide it by 32, that's going to give me an answer of 4.7 slugs. Okay, only 2 significant figures because acceleration due to gravity only has 2. Very similarly, if I'm going to do it in the metric system, I know that his weight is 672 newtons. And so if I want to calculate his mass in kilograms, I have to use an acceleration due to gravity of 9.8 meters per second squared. So then when I solve this equation for m, divide both sides by 9.8 meters per second squared, I'm going to have a mass of 69 kilograms. Okay, so that's example 5.2. So then if I look at example 5.3, an object weighs 3.42 times 10 to the third pounds on Earth. How many pounds will it weigh on the moon? Well, we had said earlier that mass is not dependent on location, but weight is. And so I know that the weight is going to be different on the moon than it was on the Earth, but I know that the mass is going to be the same both places. So if I know that he's 3.42 times 10 to the third, that's the same as if I have weight equals mass times gravity, it's going to be 3,420 pounds. And this is going to be on the Earth, just to specify. So this is on the Earth. His mass times the gravity of 32 feet per second squared, since I'm in the English system. Divide both sides by 32, and he is then going to have a mass of 110 slugs. So now that I know what the mass is of this object, I'm now going to take this object and I'm going to move it up to the moon, where I know the mass stays the same, but the weight changes. So on the moon, weight equals mass times gravity, so the weight is going to be 110 slugs. And it tells me that the acceleration due to gravity is only 5.3 feet per second squared on the moon, which is substantially less than it was on the Earth. So then when I multiply those two numbers together, that gives me a weight of 580 pounds. Okay, so you can see a drastic difference between the 3,400 pounds that it was up here and the 580 pounds that it is when it is on the moon. And that answer is logical because we know that things weigh substantially less on the moon than they do on Earth. Okay, so that's a discussion of weight versus mass. You'll be working some problems like that to make sure you can do it on your own.